So in this talk, I'll talk about the ISS Q compensation algorithm. So the Q compensation in the subsurface damages the reflection data, and the Q compensation is to recover the damage and to output the data as if it has never experienced the Q absorption. And the previous ISS Q compensation algorithm proposed by Yanglei 2010 is the only Q compensation method that doesn't need to know or estimating or determine Q. But in the previous algorithm, it requires low zero frequency data, which is impractical. So in this work, we reformulated the previous algorithm so the reformulated algorithm doesn't need the low zero frequency data, which makes the reformulated algorithm more practical. So first, I will give a review of the previous ISS Q compensation without Q algorithm proposed by Yanglei and 2010. And next, I'll show you how can we reformulate the previous algorithm, and so that it doesn't need low zero frequency data. And finally, I'll show you a numerical test. So let's start from non-absorptive wave equation for the reference medium. So the first equation is a non-absorptive wave equation. And the second equation is a two-parameter absorptive equation, where here x is a depth. So we can define the operator in this bracket as L0 for the reference medium and L for the absorptive wave equation. So the perturbation V is L0 minus L, as we see in these two equations in the brackets, L0 minus L. And then it's approximately omega squared over C squared times alpha minus 2f beta. Here alpha is 1 minus C0 squared in the reference wave speed divided by C squared x, and beta is 1 over Q. So, following Weglein 2003, the wave in the inverse series, the perturbation V can be expanded as a series, as V1 plus V2 plus V3 and so on. So here each term, the Vn is the portion of the perturbation that is the nth order in the data. So for this specific Q algorithm, for this specific Q compensation, we can write the perturbation V in terms of alpha and beta. So here is the inverse series for V in terms of alpha and beta. So Yanglei and Lira, they found a closed form of a selected set of contributions to V, benefiting from the ISS depth imaging subseries. So here is shows they found a closed form. On the right hand side is the linear term, which is related to the input data, and the left hand side is the selected set of contribution to the perturbation. And so they in Yanglei and Lira 2010, they isolated a part from contribution to V, which is only related to beta 1. So beta is 1 over Q. So beta is in the fold series. Beta is responsible for the Q absorption. So in the inverse series, here beta 1 is responsible for the Q compensation in the inverse series. And we isolated the term only related to beta 1 and avoid using alpha 1 term. So actually this isolated term is shown here. So this is the Q compensation algorithm proposed in Yanglei and Lira 2010. The right-hand side is a linear term, which is basically the data. And the left-hand side is the predicted, is the output, which is the data after compensation, after the Q compensation. In other words, this is the data we recovered the damage. So this is the data generated from the same model as if it has never experienced Q absorption. So as we say, in this Q compensation formula, we need the input data. This part, the alpha 1 minus 2f beta 1 is the input data. And we can say in the formula we need the beta 1. So in order to calculate the linear term beta 1, in the Weglein 2007 proposed the following method. So the data related to the linear term, as we show in this equation shown here. So in this equation, alpha 1 and the beta 1 is a function of the kz is the vertical wave number. And here theta in the data is a free variable. So we can choose two different theta, which is the input, which is the incident angle for the plane wave, theta 1 and theta 2. And we can combine these two equations to solve for beta 1. And here we can say, and in the previous algorithm, we can say here there includes the integral of beta 1. So this integral is to calculate this integral, the zero frequency or the low frequency of low kz or zero kz component of beta 1 is crucial. So again, this equation is used to calculate beta 1. So we can say for the low kz or zero kz component of beta 1 is related to the low zero or zero component of the data at two different incident angles. And for this data at two different incident angles, theta 1 and theta 2, in both cases, the vertical wave number is omega times cosine theta 1. And here, no matter which theta 1 you choose, the kz equals 0 is determined by omega equals 0. So the requirement of low zero frequency data made this earlier approach impractical. So next, we will reformulate this previous algorithm to avoid using zero or low frequency data. So this is the reformulated algorithm to calculate the beta 1. So basically, we reformulated the algorithm from kz theta domain to kz kx domain, where kx is the horizontal wave number, and kz is the vertical wave number. So we can choose two different horizontal kx, which is kx1 and kx2, and combine these two equations to solve for beta 1. So in this case, after we've reformulated this algorithm, so if for both kx1 and kx2, the kz equals 0 component is no longer related to omega equals 0, the zero frequency component of the data. Because here, if kz is 0, then omega is not 0. So after we've reformulated this algorithm, the reformulated algorithm doesn't need to, zero frequency data. So here is for comparison, the previous Q compensation without the Q algorithm. The kz equals 0 component is determined by the frequency equals 0 component of the data. And after reformulated the previous algorithm, now the kz is no longer related to the zero frequency data. And here is the reformulated equation to calculate the compensated data. So that is one more thing we need to look at. That is, after we reformulated the algorithm, the kz appears in the denominator in both in this equation. And to avoid the division by 0, we add a small imaginary number to kz, which means adding a small amount of friction in the reference. So we can avoid the division by 0. So next I'll show you a two reflector model for Q compensation without Q. So here it shows a 1D model with two reflectors at 100 meters and 250 meters. And the left-hand side shows the data generated from the data with Q. So there are two primaries. As we can see in the model, the second layer has absorption. So the amplitude of the second primary has a very relatively small amplitude. And the middle picture shows the data after Q compensation. We can see after Q compensation, the second primary has been recovered. And the right figure shows the data generated by the same model, but without Q absorption. So we can compare the data after Q compensation and the data generated with no Q model. So we can see they are very close. And we can take a closer look for one trace. And we will zoom in this section from 3.2 seconds to 3.5 seconds. So the red line is shows the second primary in the data with Q. And the green line is the data with Q after Q compensation. And the blue line is the second primary generated from the model with no Q, without Q in the model. So we can see after Q compensation, the green line, it looks very similar to the data without Q. So in this work, we reformulated the previous ISS Q compensation algorithm without Q. And after reformulation, the new algorithm doesn't need or require low zero frequency data. And this new approach contains two contributions. That is, first, we reformulated the previous algorithm from kz theta domain to the kz kx domain. And then we avoid the division by 0 by adding a small friction in the reference. And we also test the algorithm in a two-reflector model and obtain an encouraging result. And also this algorithm and output could also be used together with the original data to estimate Q, or use a series to calculate the beta 1 and then estimate Q. So this advance in ISS Q compensation also has an immediate and significant possible consequence for all amplitude analysis, including ISS depth imaging, ISS direct parameter inversion, and the traditional iterative AVO and model matching FWI. And the ISS Q compensation without Q method and can be transferred to electromagnetic applications where conductivity plays the role of Q. Thank you.
Any questions? So the reformulation, if you want to, you're in an elevator and you have to explain it. In other words, the data in 1D pre-stack is essentially a shot vector. So there's a function of x and t. The function you're using is a function of one variable, beta 1z. So there's a free variable, and depending on that choice of free variable, if you say linear in the data, that free variable, that choice is going to determine what the data is. Fixed theta, fixed kh is a different data. And in fact, not even fixed theta for different thetas is a different data. Just change the theta. and the linear in respect to that. So, as Dr. Yanglei said, instead of, if you formulate it in terms of theta, and many applications, including within our group, all of our ISS depth imaging, Simon Shaw, Chris Inman, Feng Lu, all were doing KZ, basically omega over C cosine theta. And to get KZ is 0, which you need absolutely, yes? You need omega is 0, no matter what the theta is. And there are approaches which are topics of discussion about what that meant, yes? What that omega is 0 that was provided in some of those tests. This avoids that issue, because here the relationship is Kz is the square root of omega squared over C squared minus Kh squared. So you can fix a Kh and get a non-zero omega, and Kz will be 0, dead 0. And it's Kz equals 0 that parameter needs to have, not omega, yes? So that reformulation means you're choosing a parameter to be fixed that will allow Kz to become, to reach a 0 value without requiring omega to have a 0 value. Now, we all know that we're very happy that Professor Mark Meyer is here and is forming a consortium soon on acquiring lower frequency data. An issue that Dr. Yanglei made clear, when you take Kh small in this new parameter, it becomes box-like sooner. Yes? In other words, a larger Kh, we don't doubt that it will work, but the initial figures, linear, quadratic, look different than for small Kh. So there's some it looks near-term advantage to choose the Kh small. To choose Kh small, you can get Kz to 0 for smaller Kh if omega is smaller. Because we need Kz is 0, and it's the square root of omega squared over C squared minus Kh squared. Yes? So if you want smaller Kh and you want Kz equals 0, you got to have lower omega. So that speaks to the value of the kind of data that Professor Mark Meyer wants to collect. Yes? Brings an allowance of choosing the parameter Kh to be smaller, which initially looks like there's some advantage. Yes? In terms of getting that Q compensation efficiently towards its goal. So, again, congratulations. In the original, where it was Kz is omega over C cosine theta, the problem there was we couldn't get Kz is 0, because that needed omega 0. The algorithm there never divided by 0, never had a 1 over Kz. Okay? When it's reformulated in terms of fixed Kh, it doesn't have a problem getting Kz equals 0, but suddenly the algorithm had a division by 0, 1 over Kz. And as Dr. Yanglei said, that was addressed here by putting a small amount of absorption in the reference, which is realistic, yes? In other words, why make the reference medium just homogeneous? Make it homogeneous with some small absorptive part, and that calms the algorithm. That's very common. Yes, resonance, right? A spring goes crazy, and resonance, you put some friction and calms down. That's what happened here. So the new parameter fixed the issue of getting Kz down to 0 without omega 0. The algorithm then had an issue, a small amount of friction in the background addressed that. And that's the result. So this is the beginning, and we plan to, so in terms of depth imaging, the ISS depth imaging, first, there was some progress. There was a result on field data. There was an issue of 0 frequency there. There was an issue that to be a practical tool we had to do multi-parameter, yes? We had to be able to exclude density-only reflections, and so on. That brings in a lot of issues. You have to gather a lot of inverse scattering, terms to deal with multi-parameters, yes? So there was a set of issues that needed to be addressed. The Q, without Q, is mimicking, in fact, ISS depth imaging, because the issue of Q cares about duration. In other words, the longer the layer that's suffering absorption, the more the algorithm has to work. The bigger the layer with the wrong velocity, the more the depth imaging algorithm has to work. Has to work means more it has to do, more terms it has to supply. That similarity allowed a transfer in an lira, yes, of work for depth imaging to this problem. The similarity in the type of task that was being addressed. Okay? That's being, that pioneering contribution is benefiting us, yes? We're benefiting, we're avoiding some of the issues and pitfalls here to make it practical. Well, thank you for today. We're going to start again tomorrow at 9 o'clock. Again, the Remembrance Sticks here. Please remember the dinner tomorrow night. You and your families are invited. And we'll see you tomorrow at 9 o'clock.